Okay, today we are talking 6.5 log functions. So we're going to convert between exponential and logarithmic form. So exponential form is b to the y value equals x, where b is the base, y is the exponent, and then x is the multiple. We can rearrange this equation to get the exponent by itself. When you do that, it's called the logarithmic function, and it's written as log base b of x equals y, where b is the base of the log, x is still the multiple, and then it equals the y value, which is your exponent. You can switch between exponential and log by doing either the loop and swoop or the hook method, depending on how your teacher taught you. You start at the base, you hook over to the other side of the equal sign, you hook back to the multiple. So notice b to the y equals x. So we're going to rewrite the equation in its equivalent exponential form. So you start at the base and you hook over to the other side. So this is going to become the log goes away. You're going to get 3 to the fourth power equals hook back 81. So if you were to do b, you'd get 14 to the 0 equals 1. For part C, starting at the base, 5 squared equals x. And then in part D, b cubed equals 64. You can go the other way. This is the one the students tend to have more trouble on. So if I'm given the exponential form, we have to put it in the log form. Since it's asking for the log form, you have to write the word log. The base of the exponent is the base of the log, so it's log base 5. Then you hook over to the other side and get 125. And that equals, you hook back over to the exponent, which is 3. Let's try that again. So we're putting it in log form, so write the word log. The base of the exponent is the base of the log. Hook over, you get 1 over 9, equals hook back to the exponent, you get 2. Notice both of these equal whatever the exponent was. So for C, write the word log. The base is 16. Hook over to 1/4 equals, hook back over, you get negative 1/2. Last one, we have log base B of 8 equals 3. So common logs are when you have a base of 10. It's so common that we don't even put the 10 there. We just call it the log of x. So if you don't see a number there, it's assumed that the log base is 10. The reason the common log is 10 is because you have 10 fingers. True story. The natural log is when you have log with the base of e. When you see this, it's written as ln of x. It's actually French. It stands for logarithmic naturel. So you would think it'd be NL, but it's actually LN because of the French. Any other log, they have to give you whatever the base is. So this is a hidden base of 10, a hidden base of E, and then otherwise they have to tell you. So looking at number 3, we are supposed to figure out what value makes this true. So when you are looking at this, I could say that this equals x. So I do the hook. 8 to the x power equals hook back 64. What number will make this true? So 8 to what power is 64? The answer is 2. You can put x equals 2 or just 2. It doesn't really matter. For part B, put it equals to x and then do the hook. 3 to the x power equals, hook back over, 27. What number makes this true? 3 to what power is 27? The answer is 3. For part C, put it equal to x, do the hook, 2 to the x power equals, hook back over, you get 1 over 8. So since this whole number became a fraction, I know it has to be negative. It's a negative what? So 2 to what power becomes 8? That would be 2 cubed, but it has to be a negative 3 to flip the whole number. For part D, the hidden base here is 10. So then we do our hook, 10 to the x equals 100. And notice the number 2 makes that true. For E, put it equals to x. You have 1/5 to the x power equals, hook back over, 25. So notice you're going from a fraction to a whole number, so you have to flip it. So it's going to be a negative number. And then 5 to the second power is 25. So this has to be a negative 2. For F, put it equals to x. Do the hook. 6 to the x power equals 1. How do you make a number to the value here equal to 1? Well, that would be 0, because any number to the 0 power is 1. For G, we could put equals to x. This one has a hidden base of e. So e to the x equals, hook back over, you get e to the 4th. The number that makes that statement true is 4. For H, equals x. Hidden base is e. E to the x equals, hook back over, you get e to the square root of 7. The number that makes that true is the square root of 7. For I, we have a 2 in front that's going to drop down and get multiplied to whatever this log is. So if you go 5 to what number is 5, this becomes 1. So 5 to the x equals 5 is going to be 2 times 1. 2 times 1 is 2. Same thing over here. The negative 4 is going to drop down and get multiplied to whatever this is. So you have 9 to the x equals 3. Well, this isn't a fraction, so it's not a negative number that'll make this true. Instead, notice we took the square root of 9. And remember, the square root of 9 is the same as having an exponent of 1/2. So this is going to get you 1/2. So it's negative 4 times 1/2, which is negative 2. For K, we're going to drop down the square root of 5. We're going to put the hidden base 10. 10 to what number is 10? So this is 1. So you have the square root of 5 times 1, which is the square root of 5. For L, there's no number in front to drop down. We have 2 to the x power equals negative 4. There is not a single number that would make this work. So this is undefined. You can't take the log of a negative number. Won't work. So these you would just type into your calculator. You should have a basic log button on your calculator. So if you type in log 33, you should get 1.5185. If you type in log 100, you should get 2. You should also have a natural log button right below, typically, the log button. So the natural log of 1.26 is 0.2311. And then if you type in the natural log of negative 3, you should be getting an error because, again, you can't take the log of a negative. So this one is undefined. Inverse functions, remember that they have symmetry with y equals x, which is the diagonal line. It ends up that exponential and log functions are inverses of each other. So we're going to use that fact in these problems. So since this is exponential and we're trying to find the inverse, we're going to convert this to a log. So the inverse is f to the negative 1 of x equals log base 6 of x. For this one, it's f to the negative 1 of x equals, this will be log base e, which is the natural log of x. Well, for c, it's not animated. So if this is log base 4, the inverse will be the exponent form, so 4 to the x. And for d, converting this would become 1/3 to the x. So we're going to use this fact to graph logs. So the steps to graph logs. First step is to identify the parent and inverse graph. I do this for you, so it makes it pretty easy. Step 2 is to make a table for the exponential graph. Then you switch the x and y table for the log graph since x and y have the symmetry. Then you identify any transformations on the log. Are you going to shift this log table up, down, left, right, or flip over the x-axis? Find where the asymptote may have moved, and then you graph. So let's put this together. So it says to graph the following on the same graph. So notice these two graphs are inverses of each other. So we're going to fill in the table for 2 to the x power. So I'm going to do 0, 1, and 2. That's what I always use. So 2 to the 0 power is 1. 2 to the 1 is 2. 2 squared is 4. So I can graph those points and notice that's exponential. To find the log, you switch the x and the y values. So 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. If I graph these points, I have 1, 0, 2, 1, 4, 2. It's going to be curving like this. So notice there's no shifts on the log graph, so it's going to stay exactly where it's at. And notice you have symmetry with the line y equals x. That's how you know you did this correctly. So there's that symmetry. Notice the asymptote for logs is the y-axis. So for part B, filling in the table 0, 1, 2. We have 3 to the 0 power, which is 1. 3 to the 1 power is 3, and 3 squared is 9. So we can graph those points, 0, 1, 1, 3, 2, 9. Now we flip our table, so this is going to become 1, 0, 3, 1, and 9, 2. When I graph these points, it's going to look like this. But when you look at the function, notice this is being shifted. So you're going to do what we always do. It's opposite, same. So we're going to go left 4, up 1 from each of these points. So left 4, up 1, put a dot. Over here, left 4, up 1. Over here, left 4, up 1. Notice the asymptote is no longer the y-axis. Instead, it went left 4. So our asymptote is through negative 4. So when we graph this, it's going to go through our new points and not cross the asymptote. You must draw your asymptote when you're shifting left or right. For part C, we have 0, 1, and 2. We're going to fill this in. So we have e to the 0 power, which is 1. E to the 1 power is 2.7. And e squared is 7.4. And we can plot those points. For the natural log, you switch the table. So 1, 0, 2.71, 7.42. And we can plot those points. Notice there's no shift on the graph. And we have this symmetry here, so we're good to go. For part D, notice it's the same parent function, so it's the same table, same graph. And then for the natural log, it's this table switch, and we can plot those points. But now we have a transformation. Notice we have a flip on the x-axis with the negative in front. And then this is inside, so it's opposite, so it's going to go right 1. There's no number on the end, so we're not going up or down. So starting here, if you flip on the x-axis, that's not going anywhere. and then you're going to go right 1. For this one, it flips down and then right 1. This one flips down 2 and then right 1. Notice your asymptote is always controlled by your shift of left or right on log functions only. So since we went right 1, my asymptote is at x equals 1. So your graph is going to curve like this.